Good morning, campers. So we're back with our 840 CI project, and we're looking at some of the problems that we're having with our adapter plate and coupler setup. So the adapter plate we'll run through soon, but I want to concentrate on the coupler because this is really where my problems are at the minute. Now, this particular coupler I had machined myself, and we had found that there was considerable error in it on a run out perspective. It was in the region of 0.12 millimeters. So I found a very helpful engineering shop that put this coupler up on a very precision lathe and machined out the error down to less than 5/1000ths of a millimeter. That's not an inch, that's a millimeter. So the run out between the it would be the minor diameter of the splines in there and this surface where we mount our flex plate is now in the region of 0.005 millimeters. So I then came back, put my coupler back on the shaft, set up my clock, spun it over, and I'll give you guys one guess what the run out is. 0.11 millimeters. So, why is that? Well, this is what we're here to find out. And I've been looking at it and I have a pretty good idea why this is the case. But before we get into that, we need to have a closer look at this coupler. So that's what we're going to do now. So I'm going to bring you guys in for a good close-up on this guy. Okay folks, this is the back side of our coupler. And what you should be able to see, it's fairly straightforward how this was actually made. We started off with a piece of 100 millimeter diameter steel stock and bored out a hole in the back side of it here. Now this internal part that you see here is part of the original Siemens motor 2 gear drive coupler that Jack supplied to me. Now we basically cut it in two, and there's a reason for that which I'll go into soon, but suffice it to say that this piece of material here is the same as what is now inside that particular hub, and it's this side of it here which has the plain material non-spline part that fits up onto the motor shaft, and obviously the spline part here that transmits drive. So that guy is precisely an external 40 millimeters diameter. So we bored out the back of this hub to 39.93 millimeters. Obviously our 40 millimeter diameter splined component would not fit inside that bore. So what we then did was heat this up with an oxy-propane torch to expand it. And when we got to a certain temperature, not red, but I'd say getting close to it, This component just fell in. It literally just, like that, just fell in. The whole thing was then allowed to cool, so that what we achieved here is a shrink fit. So this large hub shrunk down to grab that coupler. This had also been taper bored up here at the top to a 45-degree chamfer, and we came along and basically hit that with a MIG welder just to further secure the component in there. So that's the back side of our hub. Now I should mention that before this part was actually shrunk fit in there and we did the welds, this 39.93mm bore was then internally chucked on the lathe, so that all further machining was done with reference to that bore. So to flip the coupler over, what do we have? Well, we have a nose here which is 15.5mm long, which fits inside our flex plate, and it has a external diameter of 40.02mm. The flex plate is precisely 40mm, but we've a little bit of an overage on this guy just to let it be a tap fit in to the flex plate to ensure that we have a tight registering surface. This was machined, and this surface here machined again with reference to the 39.93mm bore on the back. The final bit of machining was to machine this internal diameter here to precisely 32mm, which is the diameter of the nose for the torque converter, which basically, I'll show you guys that later. It's a kind of a tapered cone that basically will just sit in there and just locates the torque converter precisely inside that surface. Before we dropped in this component, a washer was dropped in. It's a 8mm hole inside. Probably don't know if that's going to come out too well, but should be able to just make it out there. And that is so that we could put a screw inside here to thread into the Siemens motor shaft to pull the coupler back up tight onto it. Once that machining had been completed, the flex plate was mounted on here. The 9 holes for the mounting bolts were located with location punches, which I have demonstrated previously, and were drilled out to 10.5mm and tapped out to M12 by 1.5. A few of them around here somewhere for our factory flex plate mounting bolts, which basically just thread in. Now, as Magnum PI used to say, I know what you're thinking, but you're wrong. You're thinking, kind of know where the problem is here, Damien. The problem is that when you drop this guy in here, you had no guarantee that it was going to precisely center into that hole. Now, you'd be right and you'd be wrong, because when I first mounted this guy onto the motor, and I was getting the run out problem. That's precisely what I imagined happened. And I contacted a local engineering shop who were very good and were very helpful, and went over there last week, and we made a mandrel that fitted in here and picked up the splines. Very, very, very precision tight fit in there. We then came along here, built this back up with some weld, and remachined the entire coupler, referenced not to just the borehole that was in here, but to the actual splines. And the run out on all of these surfaces with respect to those splines now is less than 0.005 millimeters, which is basically nothing. Now, next thing that we do is we come along and we mount it back onto our Siemens motor. So let's remount our coupler. Onto our trusty Siemens splines. It does take some manoeuvring to make them engage, which did for one point make me think there was a king spline on there, but I don't think so. And because we're on camera now, it'll be really difficult to make it engage. There we are. So we get a nice thump, which means that our back end of our coupler is now pressing up against the back of the shaft. Who is the man? So I'm going to get our screw, put that in there, tighten it up with a hex key. Just roll this guy over a little bit. Looks good so far. Now, this is where the fun starts. Bring our clock in. I'm going to reorient the camera so you guys will be able to see this. Might as well all share the pain. So, unfortunately, I probably have the world's worst clock stand. If anyone knows where to get a decent one, please let me know, because all the ones I can find on eBay are these Mickey Mouse type. So, let me get this camera in a different position. Okay guys, not exactly cinema quality here, but I think you'll be able to see it. So, our clock is now registering on the external surface here of this diameter. And we're going to just slowly rotate. Well, that's new. Now don't mind the flick. That's simply a little bit of a dimple on the diameter from the welding. And I can actually bring it up on it. Here it comes. Flick. That's actually considerably better than it was previously. So let's see where we can go here, because now this is what's very important, and unfortunately I just can't really. Let me see if I can get the camera working here a little bit better, because it's just important to see the needle on the clock here. Now, without turning the shaft, I'm just going to put pressure on the bottom of it. See that? See the way the needle is just deflecting. Now I'm going to get something. It's going to put a little bit more pressure in there. I'm going to get a crowbar. And you might be saying to me, why am I getting a crowbar? Well, we have a torque converter that's very heavy that's going to be slung off that. So, I'm putting a good bit of pressure on that. It's not too bad actually. And this sod's law, the minute I put it on camera, the thing decides to work. I'm deflecting a line which is 0.01 millimeters, which I could live with. Let me see if I can move the clock a little bit in. So that we avoid this dimple. Now the dimple won't hurt us at all when we're actually got our flywheel. You can see the dimple here. That won't hurt us whatsoever when we have the flywheel on there. Okay. So right now, it's the amount of deflection that we're looking at as I rotate the shaft around. Now, it's considerably better than what we had. It makes me think that we might be okay. Let's see how much we're deflecting here. Okay. Now, let's see where we're at. This is live, folks. Now, as I actually handle the shaft, I've got about a half a line here. So I can actually make this guy deflect about a line probably, just with finger pressure. Now we'll get to why that is soon. So let's say I'm here, I'm at 300s there, let's say. So, interestingly, my phone contract expires this month and my phone is starting to play up. Let's not go there. Now, as I was saying, we're now got our clock on this external surface where our flex plate mounts. And interestingly, this run out seems to have decreased somewhat. Now my needle on my clock, I don't know if this is going to come out at all, but it's on about 400s down here. So let's get a marker. Mark on the surface where that 400s is. Bang or abouts there. I'm up here now to about, this is very good. I've got about, my needle is swinging, it's swinging about 200s. Now, that just might be good enough for a government job. So yeah, I mean, it's probably not even. let's try something. Okay, let's go ahead and get the flex plate on here. Now, this is not really how I would have done this previously. I mounted the coupler to the flex plate and then mounted the completed assembly to the motor, and that may indeed be why we're now seeing better run out characteristics. So let's try that theory. I have ordered a finger clock which will be able to let me look at this surface here. So let's see what we get here. Unfortunately, as I say, this is a slight interference bit. Ringing my bell. I'll line up two of the bolt holes, and we should be able to use two mounting bolts to draw it back down onto the coupler face. Now, I'm going to take a bet with you guys, and I haven't done this before, so you guys are seeing me doing this now pretty much live. I'm going to bet that run out is going to get worse. What I'm doing here is I'm just using two of the mounting bolts just to draw the flex plate down onto that surface. It's not very tight, but it's just a nice, it's probably actually less tight than the engine crankshaft, because when we were taking this off the engine, we had it out of the car, it was tricky to get off. Okay, those two bolts are now comfortably bottomed out. They don't have to be really tight, we're only hand spinning. And as I actually spin the flight wheel, flex plate, whatever you want to call it, there is almost no what I would call in-out run out on this, so I can't actually see the teeth on the ring gear or on the reluctor ring here running out, probably because we're down to those few hundredths as we saw on the clock gauge. But what I am seeing is a little bit of in-out, or sorry, this way. Probably not making much sense, it's been a long week. Sorry about that. Now, I'm looking at this and I'm beginning to say, okay, have we got a bit of an issue here with the flex plate itself being a bit out? I don't know. But just spinning it up, there's almost no perceivable run out on that plane. Now, I still think we might be in a spot of trouble here. And I want to exacerbate something here so that you guys can actually see it. So let's get in a bit closer. Now, I'm going to slightly loosen our little screw here in the middle. I'm just going to back it out a half a turn. I want to show you guys something. See this? wobble, wobble, in and out, up and down. It's all over the place. See this? Probably can't see it, but you should be able to hear it. Okay, why is that? The reason that is there comes back to something that I said in the last video about these splined couplers are designed to transmit drive. They're not designed to locate. I think that's potentially where we're having difficulty, in that the manufacture of this coupler is such that those major splines do not necessarily bottom out on the minor diameter of the motor shaft. Now, you can kind of come along to me and say, well, that might be well and fine, Damien, so, but if we just come along and tighten up our friend here, you know, and there's no more play, I can wrench the motor around. But I'm not 100% sure about that, because the play is still in there. Now, what happens when I come along and I take this big heavy torque converter and I bolt it on there like that? Because that's quite heavy, there's a lot of mass in it. Now we've got oil on my hand, and we've also got a levering action going on here, because we've got this weight levering those splines in there, and our little screw that's doing a brilliant job there now with just the flex plate may not do such a brilliant job when the torque converter is bolted up and spinning at 5,000 RPM. I don't know. But we're going to have to find out. And the best way to find out is to actually try it. Now, there's a few things that might work in our favour here, I'm not 100% sure. The first thing is that this is a flex plate. So why is it called a flex plate? Well, it's called a flex plate because these fingers where the torque converter bolts up to flex. See this? Flexing. That's a separate piece of metal to the actual flywheel part. Let's say the flex plate flexes. It does this because, let me see if this is on the camera, yeah. It does this because it must keep this pump drive engaged in our trusty gearbox. And so, the design of the bell housing as it relates to the engine will be that these springy surfaces have a little bit of forward pressure on them. So they're slightly pressed forward, keeping that pump drive engaged at all times. Otherwise, this would, it could potentially slide around a bit. So, we have presently got a little screw in here, as I say. Now, unfortunately, that screw is it's a little bit of a cap head on it, so it sits up too proud of the washer in there. I need to get a countersunk head screw, which I'm going to do the next few days to put in there. And hopefully that will let that screw sit in there so that we can bolt this guy up with the screw in there. And if we get this in, we are going to have to do some work on the adapter plate, which I'll show you now in a second. And we have a little bit of pressure on these fingers. We might have enough pressure on that spline mating against the surface in there to keep it centred up. But it is a concern for me, and it's a bit of a worry. Now what I'm going to do is I'm going to whip off the flywheel here. And I'm going to show you guys a few of the mods that we're going to need to make to the adapter plate in order to get this thing bolted up. And I think what I will do then is I will run through milling down the spacer blocks, which I'll show you in a minute. And when we have that done, we will bolt this guy up and see if we can finger rotate the assembled flex plate, torque converter and gearbox. Now what do I mean by that? Well, I had this guy bolted up previously. I had a few things going on here. I had my own error in the coupler, which we're aware of. But additionally, just bring you guys around here. Around the back of the motor here, you can probably see it a lot better. Okay. Let me get a bit of light on here. Okay. Our main adapter plate is the same piece of 20mm aluminium that we use for our existing design with the DC motor when we were testing and designing our gearbox controller. So that's just that guy, plain as. It has an additional 50mm hole drilled here to let me get at the flex plate bolts or torque converter bolts, so I can put them on when we have the plate and motor mounted up to our bell housing. So that's what this hole here is for, because the original hole that we had is now buried in that part of our Siemens motor frame. So next thing we did was, obviously this wouldn't by itself provide sufficient spacing for the coupler and bell housing flex plate interface. So we came along and took two pieces of 70 by 20 aluminium bar, cut them to size, drilled them through, and were bolted through onto the adapter plate with some M12 stainless bolts on the four mounting bolt points on our Siemens motor. Problem: our adapter plate is too far forward, so we're not getting the necessary gap between the front face of the adapter plate and our flex plate. So we need to come along, disassemble this guy and mill down probably about 3mm off the surface of these spacer blocks. So that's our next phase of the operation. When we have that done, I can then come along, assemble this whole thing up, and we'll see just how it looks. But the real test for me before I even spin the motor will be to see if, when I install my flex plate bolts, so I put in a bolt here, and I just turn this guy just by putting my finger through the, here I'll bring it around this side, you can see it better. So when I engage the first flex plate bolt, the assembly is now tied up, so I can't get near this, so I'm just working from here. So I'm going to put in a bolt here, then I'm going to use my finger to rotate the assembly through 90 degrees to get to the next bolt. Then I'm going to flick it on and so on until I get all four of the torque converter flex plate bolts in here. So I'm in. Now, problem was, when I did this last time, I put in one bolt fine, I flicked it on, put in a second bolt fine, as I was flicking it on, it was getting tighter. When I got to the third bolt, I was having real difficulty turning. And eventually I had to use a screwdriver to turn it around to get to this last bolt. But then, when I flicked it on, it became light again on these two, then it was getting heavier and so on. And what that was, is it was this in-out motion was causing the torque converter to basically bind. And if I had spun that up, we would have probably broken the hell out of it. So, next part of the plan is whip this guy off, take off our adapter plate, and we're going to mill these guys down by about 3 millimeters. I'll get the exact distance I need. We're going to shove this torque converter back into the gearbox. I'm going to reassemble all this stuff. I'll run you guys through the procedure that I have for lining everything up to get this set up. And we will then see if we can live with what's there in terms of the error, and see if we can bolt up our motor and gearbox. And if all of that were to go to plan, we'll be able to spin it up. But let's not go there just yet. Let's see if we can turn it by hand first. So stay with us, folks. Thanks for watching.